Hello, everyone, and thank you for having me. I realized today is actually the third year of being at the Ray conference, so I thought I would wear the Ray hoodie to prove it. I was here about 3 years ago in the Hyatt the other time, and since then been building stuff with Ray. So today I'll be talking a bit about synthetic data generation, and particularly a pattern about how you can combine Ray data, Ray serve, and vLLM in an easy-to-maintain way that will scale to arbitrary size data sets. Okay, hope you can hear me better now. So before we go into that, I'll just give you a brief overlook of the agenda. I want to spend some time talking about LiquidAI as well. And that's going to motivate the types of challenges that come when you generate data at scale. Then we'll jump into the main topic, which is the scalable data factory pattern that we can combine these three goodies with. And I'll try to leave some time at the end for questions as well. But to manage expectations, what I'm trying to focus on here is in this quote here I've put to give a man a fish and you can feed them for a day, or you can teach them how to fish and feed them for a lifetime. I want to focus on the fishing part, which is design principles. And we'll try to steer away from the individual fish, which is which exact data you're generating. So with that ado, let's talk about data at Liquid. We are a foundation model company, about 2.5 years old, spun out of MIT CSAIL. So what we focus on is building foundation models with custom architectures, meaning that we train them end to end and bring under one roof expertise to ship clients' models that can run on their devices, in particular edge devices, in a high performance deployment. We have already shipped a series of models. The most famous ones listed here across text, image, and audio. My favorite demo about these is probably the one where we run these on a Raspberry Pi with a high throughput. So that gives you a sense of what we're able to do at Liquid. We can run these models at embedded devices at real-time performance. So what goes into this when you train edge models and pushing the frontiers on those? Well, you need to manage the full stack of data. So starting with pre-training data, we're talking petabytes, trillions of tokens that go into the pre-training. Slowly but surely, we start mixing in templated data for chat and downstream purposes. So now the focus starts shifting towards quality and more specific use cases. At the very end, there's the post-training phase where the quality of the data is really essential. And there's a large compute budget allocated to just making sure that this distribution is really matching downstream tasks and aligning the preference of the model to where we want it to be. So as you can see, there's kind of a mix of things that we need to consider. We have some tasks that are very I/O and CPU bound, some tasks that become increasingly GPU bound, and towards the end of the stack, it's really a very GPU-bound, intense patterns that are needed to generate this synthetic data that aligns the model preference. So this needs to scale to petabytes because of the early stages. It needs to handle complex generation patterns, so things where we can develop arbitrary orchestrations of multiple models together. And quality assure the output. And while doing this, we need to consider that AI is moving very rapidly, so iterations need to be very quick, and we want to future-proof our code so that we can quickly onboard what is happening in the field in general. We want to be able to add new models quickly and add new patterns of data generation to our code base without making major revamps of the code. So this kind of feeds into the considerations that we're going to talk about when designing data pipelines. We need things that scale up, handle complex patterns, and are future-proof to what goes on in general in the industry. So let's go into that right now. How do we do this? Well, I'm going to show you a simple pattern. I've made here a very simple workflow. We get input text. We translate this input text using a language model to some other language. We use a separate language model, a judge, to score whether this data is any good. If the answer is yes, let's collect it. If the answer is no, let's feed it back and reiterate. We can try this, let's say, 3 times until we discard the sample and log it as failed. So recalling about the fish and fishing here, this pattern, the fish, is not what I want to say is interesting, but how we can design this and implement it here in a way that scales up to arbitrary size of data. The input text will have to be read in, parsed, and then put through this loop and written. But that input corpus could be larger than fits into memory or even on a single machine. We also have 2 models, so we need to orchestrate 2 models there independently. Considering that this data could be very large, we have to consider that those 2 models might have different resource requirements. Over time, we might want to update those models in different ways, taking on new models as we train them or as we onboard them from other sources. How can we do this with simple code that's maintainable and easy to debug? Well, let's start off with the LLM deployment. Our friends at RayServe have written an excellent plugin to vLLM that lets us, in these few lines of code, define LLM configs that define a translator and a judge model. It's abstracted away what those models are through the model source. It's also abstracted away what the interface is. So when we go ahead and deploy these, RayServe will wrap them in an OpenAI compatible API, which means that we could even forget that these are actually running in vLLM. For all we know, they're hidden away behind an API that we can call with a simple asynchronous client. So furthermore, since we deploy them with vLLM, we get the continuous batching for free. And when we wrap them in RayServe, we're able to scale these things independently. So RayServe will allocate resources according to the usage pattern and scale them up and down as necessary. So what we get for free is the load balancer, the auto scaling, and the continuous batching that vLLM implements. So we have now effectively abstracted away the choice of language model behind a very efficient implementation that scales both in terms of replicas and implements efficient inference for the language model without having to worry about which language model it actually is. So this means that we can call them through an OpenAI client. So when we go ahead now and define our translate and judge functions, all we need to pass to these is the OpenAI client. And for the translate function, we'll pass along the text, the language that we want to generate, the translation target. And there's that feedback variable that will come in useful in case we need to iterate on it. For the judgment, I've chosen to do a structure generation. It's easier to parse, makes the code a little bit more clean to write. So this one will deem whether the translation is any good, and if the answer is no, there's a comment that we can use for feedback for trying again. So now we've implemented the 2 parts of the control flow that we want to link together. Note that the judge and the translator are just passed in the model handle to these clients. So we actually, in this part of the code base, don't have to worry at all about which models it is that are actually running that computation. For all we know here, we can consider it done. And the maintenance of the models and the updates over time for is future-proof in the configs that we defined earlier. Now, let's have a look at how this control flow runs. It's on a single piece item. So because it's asynchronous functions, we can easily debug them by just passing a single text as input and observing the single output there. But because they're asynchronous, we're able to run multiple of these concurrently, multiple texts through each of the function at the same time. So throughput is not an issue. There's no heavy computation done here. It's all offloaded to the vLLM server. So let's have a look at the last page, which is the control flow. There's something very important here that I want to emphasize. So this implementation of the control flow follows the spec that Ray data expects. The call method over here is an asynchronous generator, so it will pop right into the Ray data steps that we will look at next. But this means that we can define this class here and later use it in a broader context where we can scale it up and down depending on the data needs. I'll talk more about that in the next slide, but let's first look quickly through the control flow here. So an asynchronous generator, for those not familiar with it, is going to return 0 or more items. In this case, we get one row as input. It will contain the text. And then if things go well here in the if statement, we will yield out the translation. If we iterate over max attempts, we try 3 times, for instance, to translate and judge, and we're not reaching a satisfactory judging result, we will end up here in the else and log out that there was a fail, but not return anything. So effectively, we're discarding bad data points that we're not able to come up with a satisfactory translation for. Now let's look at the Ray data integration. The magic here is just that we have the called under defined as an asynchronous generator. That's all. In the main method now, this class can be put directly into a Ray dataset, which means that just the way we offloaded all the GPU-bound operations to Ray serve, we're offloading all the CPU-bound operations into Ray data. So in this case, I'm just defining a very simple Ray data from items over here. But in a production use case, you're probably reading something from a cloud bucket, like a Parquet, and you're streaming in rows from these Parquet shards, doing some complex pre-processing on the CPU, streaming that in turn through this translation app, and finally doing some post-processing at the end before writing it to another cloud bucket. In this way, we're actually doing all things concurrently now. We're reading from a cloud bucket concurrently with Ray data. While we're doing that, we're pre-processing in a separate step. We're running this translator, which offloads all the GPU workload onto Ray serve, and then writing. And these, because they happen in different processes with Ray data, are all happening at the same time. So we're able to squeeze out every bit of throughput from both the CPUs and the GPUs and the I/O that we need to wait for both reads and write. So concluding remarks about this pattern, we're able to write code that handles individual items, but scales to arbitrary large data sizes. All happens with streaming execution, and the GPU-bound workloads are scaling up and down with Ray serve auto-scaling. We've decoupled the models as their own microservices in a way where we have reusable code that doesn't depend on the model, and we can easily update if there's a new model that we want to use or try a new checkpoint on a new translation model. We can configure that from the config without touching any of the business logic in the actual inference code. The auto-scaling solves the resource allocation. So we've offloaded the CPU scaling to Ray data and the GPU scaling to Ray serve. So these are going to scale up and down to find the optimal utilization for the compute budget that we allocate. This makes this translation workflow an example of what can be done. But what I want to emphasize here is that you can do this with any arbitrary multi-step, multi-modal workflow. You're no longer bound to exactly which implementation sits within these shells. You could have an arbitrary count of models deployed, an arbitrary count of steps applied, and because there's no assumption on a directed acyclic graph like with Ray data, you can within the Ray this step that we previously defined in the translation, you can do your cyclic logic there and apply your retries, which will scale to an arbitrarily complex data generation pattern. So thank you for listening. I hope there's some useful takeaways there. I saw some of you taking photos. I'm happy to share the slides. Just reach out to me on LinkedIn here, and I'll happily share the slides so you don't have to transcribe it manually. Should also mention we are hiring at Liquid, so if this sounds like something interesting, please do contact us either through LinkedIn for me or on our hiring page. And these are the types of problems you can be working on at Liquid. Thank you.